Hello everyone. Following up on the last lecture, I want to talk about some other things related to dealing with signed values, and specifically I want to talk about sign extension. Okay, so you may have even come across an example of sign extension when looking over chapter 7. There's an example 7.8 which talks about sign extension, but I think the best way to think about it is through the use of an example. Okay, so I'm just going to pull in a figure out of the textbook, and I think this makes it quite clear what's going on when sign extension happens. Here you see an example starting out. Let's assume we have a value that's stored in as an 8-bit value, -8 or +57, and shown and highlighted here are the associated binary values. If I store this in a let's take the -8 value for example. If I take that and just stick the value for -8 into let's say a 16-bit register without doing sign extension, I'll have a value that looks like this, and this is no longer a value of -8. Right away we can note that it must not be a negative value because our most significant bit is not a 1, which it would be if it were negative. Okay, and in fact if we do the conversion here, we discover that this is actually equal to a value in base 10 of 248. So not at all what we intended. Okay, so what we need to do when we store this 8-bit value into a larger memory space is do what's known as a sign extension. So we take the most significant bit. So first off, we have to know that our data is signed data to begin with. Once we know that, we can use appropriate functions that will do this sign extension. They'll take the most significant bit and just extend that bit into the bits that have been added from the original value. Okay, so now we have a value here that's 16 bits, but this is still equal to -8. Okay, and of course we can sign extend. In our case, we would, with an IS2, we would be sign extending to 32 bits often when we're doing reads into registers. And again, you just see that the most significant bit gets extended into all added bits, or all bits that are the value is extended by. And this works for both positive and negative values. For positive values, it's maybe less critical because if we assume all the values that get added onto the most significant positions of a extended value, adding zeros is actually not changing the weight of our value anyway. But just the same, it's good to know that it is in fact extending that most significant bit from the original value. In this case, that most significant bit again is getting extended into all positions, whether it being extended to a 16 or 32-bit value. So if we jump over to our instruction set reference here for a second, here's another example of when we need to know the data type that we're dealing with. Okay, so if we look at this load byte, so if we're reading in a single byte from memory, we would use this load byte command. But we should note here that the load byte, I can open this up so I can highlight, the load byte loads register B with the desired memory byte, sign extending the 8-bit value to 32 bits. Okay, so there's the key part. It's doing a sign extension. Okay. And again, if you look in the course notes, page 135 at example 7.8, it's worth noting that this value has been sign extended because maybe we didn't want all those extra ones padded onto the front of the value, because maybe we're going to turn around and do some 8-bit operation with that. Okay, so it's important to know the details of their various instructions. So if we look at this next load byte, here's a load unsigned byte from memory. Here you'll note that there's no discussion about sign extension happening, and this is just going to pad the additional bytes that result from putting a byte into a larger register. It's just going to do a 0 extending of the 8-bit value to a 32-bit value. Okay, so at the end of the last lecture, I mentioned the need for wanting to represent fractional values in binary, and it's maybe not immediately obvious how to do that. So when we're dealing with I want to say standard processors, they are able to kind of out of the box able to handle what's known as fixed point binary. And because the all of our arithmetic operations on a fixed point binary number still occur in the same way as they would any binary integer, fixed point binary allows us the capability to represent a decimal point within our binary number. Okay, so when we do that, so I'll give you an example here. So let's, for example, assume we have a binary number, and I'm going to use an example from the textbook because there's a nice table here to represent this. But let's assume we have a binary number that's equal to this. Okay, and that if we do the calculation, we determine that that's okay. So this is binary base 2. We can show that that's equal to a value of 201. Well, if I were to, just like with any binary number, if I were to shift those bits 1 bit to the right and assume that I can represent a decimal point, this value is in fact divided by 2. So this new value would be equal to 100.5. And you may say, where does the 0.5 come from? Well, if we think about a standard number, so in decimal, when we get below the to the right of the decimal, each of these positions to the right of the decimal represent a fraction of 10, right? So this is equal to This is equal to 10 to the minus 1, 10 to the minus 2, 10 to the minus 3 is the weight of that position. Of course, it can be times whatever value is in that position, right? So it's whatever value sits here, 2 times that, 3 times that, 4 times that, 8, let's for example, times 10 to the minus 4. Right, and if we think about what each of these represents, this is a value of 1/10, 1/100th, 1/1000th, and 1/10,000th. Okay, so we've dealt with decimals in places on to the right of the decimal in base 10 for some time. Okay, so maybe instead of calling this decimal, let me call this base 10 just to avoid any confusion. But with base 2, my positions to the right of the decimal are to a base of 2. So this position is the weight times 2 to the minus 1. This is whatever the weight is, and of course the weight can only be 1 or 0 because in base 2 I can only have a 1 or a 0. So this is times 10 to the minus 2 times 2 to the minus 2 times 2 to the minus 3 times 2 to the minus 4, which is a weight of 1/2, a weight of 1/4, a weight of 1/8, and a weight of 1/16. Okay, so with that in mind, I can represent different fractional values with what we would call fixed point binary. Okay, so if I now grab the figure from the textbook, so taking that same value that we started with and shifting it to the right 1, 2, 3, 4, 5 more times. Okay, so that's should be dividing that by 2 to the power of 5. Actually, let's just based on the original value, let's say we're shifting it 1, 2, 3, 4, 5, 6 times. So this is going to be a divide by 2 to the power of 5. Right, so if I let's say shift to right 6 times is equivalent of a divide by 2 to the power of 6, or a divide by 2 to the divide by 64. So my original value 201 divided by 64 is equal to 3.140625. Okay, so let's see if that value makes sense as if we think about the binary representation. So taking this value here and considering the weight of every position, which I now have shown here. Here's the weight of every position. This is 2 to the power 1, 2 to the power 0, 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and so on. right? And so I'm going to, down below here, say, okay, so this is 1 times 2 to the power 1, so 2 to the power 1 plus, I've got 1 times 2 to the power of 0. Okay, so 1 times 2 to the power of 0 is 2 plus 2 to the power of 0, and I go plus here. This is just going to be 0 because I'm multiplying by 0, 0 here, plus 2 to the power minus 3, plus 0, plus 0, plus 2 to the power of minus 6. 1 times 2 to the power of minus 6. Okay, so 2 to the power of 1, so this is 2 plus 1. Okay, these values are shown here. Plus 0 plus 0 plus 2 to the power of 3 is 1/8 plus 0 plus 0 plus 2 to the power of 6 is 1/64. Okay, so this is going to be 3 plus 1/8 plus 1/64. Okay, that will give us a value of 3 plus 0.125 plus 0.15625. Add those together and we get the value that we said earlier from just taking 201 divided by 64. Okay, and this might be used as an approximate value for pi, for example. But we are limited in the precision we can get based on the number of bits we might have available. So in this case we have 8 bits to represent our fixed point binary value. So our increments can only be as large as, let me just clean this up here. Oops. Our increments can only be as large as, or as small as 1/64th, and of course we can only get values integer value as large as, well, in this case 21, I guess, if this is the position of our decimal point. Okay, of course if we have a 32-bit value we can get more and more precision, but we are still limited on how precise we can get. So fixed point has its applications, and in some cases our processors are limited to only doing fixed point fractional representation of numbers, but we often want to do better than that. Okay, and that leads us to talk about floating point, and we're going to talk about a very specific standard. There's a few different standards. One of the very common standards for representing floating point numbers or fractional numbers in a computer is the IEEE 64-bit floating point format. So I just want to point out that not all processors are able to handle floating point arithmetic. The ALU may not know what to do with floating point numbers. So if you're doing some extensive calculations that require precision, you may want to ensure that you have a floating point processor available. Okay, so floating point is not limited to represent only integers, although we've now shown that with fixed point we can show fractional values, but with some limitations in precision. Okay, and this this particular standard that we're going to look at allows floating point numbers to be represented by a binary number, numbers. Okay, before we look at the structure of a of this format, let's consider a. I'm going to put this off to the side because this is not IEEE 64-bit floating point format. But imagine a calculator that has is limited to just 10 digits being displayed. Okay, so with those 10 digits we can represent values up to all nines, and if you have it in kind of the standard scientific format, it will put the first digit, then a decimal point, and then all the other points past the decimal, and then it'll show the exponent value, and that exponent value likely is limited to 2 digits, and then you often will, well, you will have the sign of the value shown, whether it's positive or negative. Okay, so even though my display is limited to only being able to show 10 digits, I can represent a huge range of values, right? All the way from plus 9.9999999 times 10 to the, I can go from, I can have values from minus 9999999. How many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8. I guess we're assuming that the exponent takes up 2 of our spots here. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the minus 99, and I can have values plus 9.99999 times 10 to the plus 99. Okay, so it can have a huge range of values represented by my calculator, even though it's only able to show a total of 10 digits. Okay, the base of that calculator display, this part is referred to as the mantissa. This part, the exponent, is referred to as the exponent, and of course we have our sign value, positive or negative. Now let's look at what the IEEE 64-bit floating point format looks like. Okay, so this is the format we're actually interested in that allows us to represent floating point numbers in a processor. So we have 64 bits available. Now we're going to use a single bit to represent the sign. So 0 will represent a positive value, 1 will represent a negative value, we have 11 bits to represent the mantissa, the exponent value, but we remember that our exponent in this system is a base 2 exponent, and then we have a 52-bit mantissa, so that base value. Okay, so how do we get a floating point number into this format? Okay, so let's work through how this might happen. So the first thing we need to do is we need to normalize and adjust the exponent until the mantissa is in this format. So our 52-bit mantissa will only have one spot, one bit or one value to the left of the decimal, and then each bit will represent my digits, my base 2 digits to the right of the decimal. And in this sense, I can go from a mantissa that's 1 point all zeros or 1 point all ones. Okay, up to, of course, I can have a total of this being all the way to 0, where this is 2 to the minus 1, and this is 2 to the minus 52. Okay, you might say, well, wait a second, you have 52 bits, you forgot about this 1. Well, you'll note that in all cases that's going to be a 1, so there's no reason to waste a bit to represent that 1. We'll just that 53rd bit is implied. Okay, so because this is always a 1 in that spot to the left of the decimal, that bit is implied. Okay, so that bit's not needed. 53rd bit is implied. Is implied to be a 1. Okay, so that's our mantissa. We'll look at an example to see how we get a value in this format here in a second. We have 1 bit dedicated for the sign. This should say bit here, 52-bit mantissa. We have 1 bit for the sign, and that's simple enough. A 0 means it's positive. And a 1 means a negative. Okay, and finally we have our 11-bit exponent. Okay, exponent. Now our exponent uses 2's complement, because our exponent can be positive or negative, and we're going to use 2's complement format to represent those values. What's interesting about the exponent is its offset to 3ff. So a value of 3ff in the exponent is equal to 0. Okay, again, we'll look at an example, hopefully help solidify what's going on here. And with all of this in place, we don't really see a means of representing a value of 0, particularly if that 52-bit mantissa, if we're applying, there's a 53rd bit that's a 1, that doesn't really allow us to represent a 0. So there's a special case to represent a 0. So value of 0 is a special case where the entire 64 bits are all zeros. Okay, so that's easy enough. Before we get into an example, let's just talk about the range of values that we are able to represent with this 64-bit floating point format. Okay, so if we consider that our exponent is 11-bit signed value, well, that means that we can have magnitudes of up to 2 to the 10, which if you should know by now, 2 to the 10 is equal to 1024. But again, remember this exponent of this floating point format is a base 2. So the exponent can be up to 1024, and it's a base 2, an exponent on a base 2 number. So 2 to the 1024, our largest exponent, if we figure out what the decimal equivalent of that is, or the base 10 equivalent, that's equal to approximately 10 to the 10 to the 308.25471566, okay, which is equal to 1.8 times 10 to the plus 308. Okay, so and the negative value can be minus. If you figure it out, you can have a negative value of minus 4.9 times 10 to the minus 307. Okay, so this is the range of values we can represent with this format. So it's quite extensive. So we can represent values quite precisely with this format. Let's look at an example of how we represent a simple decimal number using this floating point format. Okay, I'm going to use a value of 10, right, the base 10 value of 10. That value in floating point format, so the first thing we said, I had to normalize the value to a mantissa that was 1 point something. I'm going to trust me for a second that the mantissa for this needs to be 1.01. Okay, and if we break that down, again remembering, okay, this is 2 to the power of 0 plus let's go 1 times 2 to the power of 0 plus 0 times 2 to the power of minus 1 plus 1 times 2 to the power of minus 2. Okay, so this gives me a value of 1 plus, well, this is times 0, so plus 0 plus 1 times 2 to the minus 2 to the minus 2 is a quarter, or 0.25. Okay, so this mantissa has a weight of 1.25. Okay, and quite conveniently, that times an exponent, or times a base 2 exponent that is 3, will give me a value of times 8 here. 2 to the power of 3 is 8. Okay, so this 1.25 times 8 is equal to 10. Okay, let's take this value now and put it in our 64-bit floating point format. Okay, so we have 1 bit for the sign, we have an 11-bit exponent, and we have a 52-bit mantissa. Okay, well, the sign in this particular case is a 0 because it's positive. The mantissa, remember that the leading 1 here is not needed. Okay, so I'm going to just say the leading 1 is not needed. Right, this 1 not needed, so I just need the values to the right of the decimal point, which is 0. Oops, let's go back. Let's use black here, which is 0, 1, and that's all I need. The rest of the 52 bits are going to be 0. Okay, and my exponent, I need an exponent here for a base 2 exponent of 3. Now remember, I said my exponent value is offset to 3FF, where 3FF is 0. So assuming that 3FF is 0, I add on a value of 3. I've already got this in hex here. I get a value of 0 plus 11 bits that are 402, and then my 52-bit mantissa. And if I convert this to hex, every 4 bits, so all of these bits past the first 4 are going to be 0. So I have a value in hex of 4. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros to represent the remaining 48 bits that are all 0. Okay, so in hex, my value, my 64-bit value is 402, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that floating point value is equal to a value of 10 in decimal. Okay, so that's how floating point numbers can be represented in a computer system. And again, we're assuming that we're dealing with a computer system. I mean, we could represent them in any computer system this way, but we may not be able to do arithmetic operations on them directly if our ALU is unable to support them. But in terms of storing the data in this format, the processor doesn't necessarily care what the what is in that data if we're just storing it. Here's a table from the course notes. Here's just an example of some various values stored in our 64-bit floating point format. Maybe you'd like to go and see if you can work yourself backwards from that 64-bit floating point format to convince yourself that they're equal to the decimal values on the right, just as just for fun. Okay, this isn't the only standard for representing floating point numbers. Just as another example, here's another IEEE standard for representing floating point numbers in a 32-bit system. One final thing I'd like to just touch upon briefly. I usually skip over this topic, but it's something you'll cover in more detail in your embedded systems class later. But that's the means of representing analog or continuous time signals in a digital system. And here's just an example of a continuous time signal, a simple sinusoid, and how we might represent it in a digital system. So there's two things we have to think about is what is the resolution of the magnitude that we can represent, right? So how many bits are we using to represent this kind of axis of the waveform, right? If we only use a single bit, we can only represent whether the data is a 0 or a 1, and it's not going to give us much ability to accurately represent this continuous time signal. With 2 bits, we can now represent 4 steps, and 3 bits, 8 steps, and 8 bits, we can represent 256 different discrete steps along the magnitude axis. So that defines our resolution, and it's a term you'll often hear used when describing analog to digital converters. But the other aspect of converting a continuous time signal, this signal is represented at every single point in time as we move along. But a digital system, a computer system, doesn't think in continuously, right? We represent things at discrete points in time, and we do operations at discrete points in time, often synchronized to a system clock. So in that sense, we also represent our analog signals at discrete points in time, and this is called sampling, where we sample every so often, and that defines a sampling period, or we can think about a sampling frequency, which is 1 over our period. Okay, so again, I don't want to get into that any more than this, and you'll talk a little bit about sampling signals in your signals class as well, for those of you that take it. But it's just good to know that there are means of representing continuous time analog signals in a digital system, and we get those signals into the system through what's known as an analog to digital converter.